In this video, we will explore various geometrical relationships between lines and planes. As with between two lines, there are a few ways a line can intersect with a plane. It can intersect at one point where the line is not parallel to the plane, like this plane and a line that looks like this. So the intersection is just at one point over here. It can intersect at infinite number of points. So I have a plane and I have a line that is contained within the plane, and therefore there are infinite number of solutions. And finally, the line can have no intersection with the plane. That is when the plane and the line are parallel to one another. To solve for the intersection between a line and a plane, we simply have to substitute the equation of the line into the equation of the plane. For example, we have this line and this plane. We simply have to replace the r vector in the plane by the right hand side of the equation of the line. Thereafter, we can expand the dot product to arrive at an equation containing lambda. The solution of this equation will give us insights on how the line and the plane intersect. If the equation can be solved to give a unique value of lambda, then we know that the line intersects the plane at exactly one point. If the equation reduces until a point when you get equal constants on both sides of the equation, for example, we can have the equation of lambda plus 2 plus lambda plus 3 minus 2 lambda plus 1 equals to 6, which can be simplified into 6 equals to 6. Then this tells us that any value of lambda will satisfy the equation. Thus, all values of lambdas are solutions to the equation, and the line intersects the plane at infinite points, or the line lies on the plane. Lastly, we may also have the case where the equation is reduced into a constant equals to another constant. For example, we may have lambda plus 2 plus lambda plus 1 minus 2 lambda plus 1 equals to 1, which reduces into 4 equals to 1. Then this means that no matter what value of lambda we choose, the equation will never be satisfied, and thus the line will not intersect the plane. In example 1a, we have the line L1 and the plane pi. So to determine whether the lines and the plane intersect, we will have to do a substitution. First, we'll change the equation of the plane into scalar product form r dot 1 equals to 1. Now we can substitute the equation of the line into the equation of the plane, and this gives us 1 plus lambda, 2 minus lambda, 3 plus 2 lambda, dot 1 equals to 1. If we expand this dot product, we will get 1 plus lambda plus 2 minus lambda plus 3 plus 2 lambda equals to 1. And on solving, we will get a single value of lambda at -5/2. And this tells us that L1 and pi1 intersect at one point. Now, if we are interested to find out the coordinates of this intersection point, we simply have to substitute the value of lambda into the equation of the line. So we get r equals to 1, 2, 3 plus -5/2 multiplied by 1 minus 1, 2, and this gives us -3/2, 9/2, and -2. And we can say that the intersection point is -3/2, 9/2, -2. In example 1b, we have now the line L1 and the plane pi2. So first, I will write down the equation of pi2 in vector form. R dot 1 minus 1 minus 1 equals to -4. And now I can substitute the equation of the line into the equation of the plane to give me 1 plus lambda, 2 minus lambda, 3 plus 2 lambda, dot with 1 minus 1 minus 1 equals to minus 4. And if I expand, I will get 1 plus lambda minus 2 plus lambda minus 3 minus 2 lambda equals to minus 4. And on simplifying, the left hand side becomes minus 4 and the right hand side remains at minus 4. Now this tells us that there are infinite number of solutions, and therefore L1 lies on the plane pi 2. In example 1c now, we are going to compare L1 and pi 3. So same thing, pi 3, I'm going to rewrite it as r dot 1 minus 1 minus 1 equals to 1. And I'm going to substitute the equation of the line 1 plus lambda, 2 minus lambda, 3 plus 2 lambda into the equation of the plane. So I have this. And if I expand, I get 1 plus lambda minus 2 plus lambda minus 3 minus 2 lambda equals to 1. The left hand side simplifies to be minus 4 and the right hand side is still 1. So I know that whatever value of lambda that I use, this equation will never be satisfied, and therefore there are no solutions. L1 is parallel to pi 3 and does not lie on pi 3. In the chapter of vectors, when we are finding angles, it is almost always using the dot product formula, which means cos theta equals to d1 dot d2 over mod d1 mod d2. Except in the case when we are finding the angle between a line and a plane. Imagine that we have this plane now and this line. The characteristic directions that we are going to use are the direction vector of the line and the normal of the plane. And if we apply the cosine inverse formula, we will end up with the angle that is in between these two characteristic directions instead. Let's say the angle between the line and the plane is theta. That means the angle between the line and the normal vector is going to be 90 minus theta. Therefore, we can say that cosine of 90 minus theta is going to be equals to d dot n over mod d mod n. And from trigo, we know that cosine of 90 minus theta is going to be equals to sine theta. Thus, we can write down sine theta is equals to d dot n over mod d mod n. And we will also put a pair of modulus to make sure that this term is always positive, and thus we will get an acute angle. And with this, we can do a sine inverse on both sides to arrive at this equation over here, which allows us to find out the angle between a line and a plane given the direction vector of the line and the normal vector of the plane. In any case, you just have to remember that in all vectors questions, it is always using cosine inverse, except when finding the angle between the line and the plane, in which you have to change the cos inverse into a sine inverse. In example 2, we have to find out the angle between L1 and pi 1. So we can just apply the formula directly, since we know it is the angle between a line and a plane. So theta equals to sine inverse of modulus 1 minus 1 2 dot with minus 1 2 and 4 divided by mod of 1 minus 1 2 and mod of minus 1 2 and 4, which can be simplified into sine inverse 5 over square root 6 square root 21, and therefore this gives us 26.45 degrees, which we can round off to 26.5 degrees. With a line and a plane, it is also possible to determine the line of reflection about the plane. To determine the equation of the reflected line, we will need 2 points on the reflected line. The first point that we can use is the point of intersection x between the original line and the plane, since both lines and the plane will all intersect at this same point. Next, to obtain another point on the reflected line, we can find a random point, point A, on the original line, then reflect it about the plane to get point A prime. The point of reflection A prime will be a point on L prime. Therefore, we can form the direction vector of line L prime as vector A prime x, and the equation of the line is thus OX or OA prime plus mu times of A prime x. In example 3, we are given line L1 and plane pi, and we are asked to find the line of reflection of L1 about pi. So we are going to do it from scratch, and the working will be quite long for this example. Let's draw the diagram out first. I have the plane pi, I have the line L1, and I need to find out what is line L1 prime. So the things I need will be to find point X, to find the point A, and to find point A prime. And of course, in order for me to find point A prime, I will need to find out the full of perpendicular over here, point F. So first, let's find what is OX by substituting equation of the line into equation of the plane. So to find X, we can say that 1 plus 2 lambda minus 4 plus 4 lambda, 9 minus 9 lambda, dot with 1 minus 2, 4 equals to 3. And we expand this to get 1 plus 2 lambda plus 8 minus 8 lambda plus 36 minus 36 lambda equals to 3, which gives us lambda equals to 1. And therefore, we can say that OX must be equals to 1 minus 4, 9 plus 1, 2, 4 minus 9, which gives us 3, 0, 0. Next, we want to find out a point A. We can say that let point A be OA equals to 1 minus 4, 9. And the full of perpendicular is F as we have defined in the diagram. So we can say that L AF, the equation of line AF is R equals to 1 minus 4, 9 plus mu 1 minus 2, 4, where mu is a real number. Now this line is going to intersect the plane at the full of perpendicular. Therefore, I'm going to do a simultaneous equation again. 1 plus mu minus 4 minus 2 mu and 9 plus 4 mu dot with 1 minus 2, 4 is going to be equals to 3. And on expanding, I will get 1 plus mu plus 8 plus 4 mu plus 36 plus 16 mu equals to 3, which gives me mu equals to minus 2. And therefore, I know that OF will be equals to minus 1, 0, 1. Next, I'm going to find out what is point OA prime by using ratio theorem. So I have OF equals to OA plus OA prime over 2, which can be rearranged to become OA prime equals to 2OF minus OA, and this becomes 2 times negative 1, 0, 1 minus 1, negative 4, 9, which becomes minus 3, 4, minus 7. And with this, I have the second point on my L1 prime, which I can now use to find out the direction vector. So finally, I have A prime x equals to 3, 0, 0 minus 3, 4, minus 7, which gives 6 minus 4, 7. And therefore, I can say that L1 prime has equation of R equals to 3, 0, 0 plus alpha 6 minus 4, 7, where alpha is a real number.